Okay, hello everyone. Very good evening. Welcome to the week 9 of the tutorial session of the course CFD using FVM. My name is Varnit Kapoor, and I will be taking up the tutorial for today's session. So I hope everyone is doing the assignments, watching the lecture videos. And if you have any doubts at any point of time, please stop me and ask. Okay, so let us start. Already it's past 5 minutes. Okay, show here, let's join. Okay, all right. Let us start. Let me share my screen. I hope my screen is visible. I'm not sure. My screen is visible. Yes. Okay. All right. All right. Let us start. Yeah. Now we are ready to start with the session. So today's topic will be about data diffusion and unstructured meshes. Okay, which we were doing earlier also. But today we'll start with the gradient calculations. Okay, because we had a secondary gradient calculation which is need to be done so far, and how uh, delta p term in the Navier-Stokes equations it's used for that. So calculation of secondary gradient on the faces was reduced to the calculation of gradient of the scalar on the right face, okay, in the epsilon direction, right? Gradient on the face and face normal in the normal direction. So today we are going to look at the gradient calculations, and one of the reasons to calculate the gradients that its requirement of second gradient is okay. It requires the gradient of the dependent variable on the faces. And there are several other instances where the gradients of dependent variable are required. Like if we say if you have a solving Navier-Stokes equation, then we have to calculate what is pressure gradient. In the calculation of Navier-Stokes equation, we have the pressure gradient term which is needed to be calculated. And we also know that it is not just the gradient in the direction of the face that is required, but rather the gradient in all the direction. All the components of the gradient are required, like I, J, K components are required, and not in just the direction of the face. It's required by the secondary gradient. Again, if you have, you say, non-determinant model for your viscosity, then also we would need gradients of the velocity because the gradients of velocity are required in the non-determinant coefficients that needs to be calculated. So as a result, we need to calculate what are the gradients of velocity. Here you would say uh, can be phi. Similarly, if you have solving for the turbulent flows also. Let me write first this much. Gradient calculation. Okay. First scenario, secondary gradient, secondary gradient calculation required. Then gradient of P is there in the Navier-Stokes equation. Then third is your non-Newtonian model for viscosity. Okay. All right. Now again, you have turbulent flows. There is Ram's model, like K epsilon model is there. where production terms come like gradient of U, Elias model is there. Where subgrid scale stresses comes like tau I of J, which requires again gradient of U. Okay. So next scenario is in turbulent flows. Where we have Franz model, then we have K epsilon model, where production terms are there. Which involves gradient of U, gradient of U. Then we have Elias model. Or where we have subgrid scales. Like tau ij, which require again gradient of U, right? So to solve this, we have two different approaches in the literature so far. We have multiple researches are going on, but we have two commonly used approaches, which is one is gradient theorem approach or called as Green-Gauss method, and another is the least-square method. So first method is gradient theorem approach, or you can say Green-Gauss method. Okay. Another is least squares method. Let's see each method one by one. Let's start with the green gradient theorem approach. Or you say Green-Gauss method. Here, if you have closed volume that is enclosed by surfaces, like Gauss divergence theorem is there. There you have del dot of divergence of any vector dV over controlled volume is equal to F dot N dA. That is dot product of the vector with the area vector, okay, over a closed surface. But here, if you have a closed volume that is enclosed by surfaces, that is enclosed by surfaces. You can say gradient of effect property phi over the integral EV and del V naught is equal to over the control surface phi of dA. Okay. All right. I hope it's clear. Gradient in the gradient theorem, it's in the gradient theorem is for gradient of a scalar integrated on a closed volume, and we are considering a closed volume, right? That is enclosed by surfaces. So these surfaces are enclose it completely. Close the volume, and there are no openings. So we consider a cell of to be the same property then of a closed volume delta V naught. And what would be the gradient theorem say, or Green-Gauss theorem says that we have a delta V naught volume. In the volume, we want to calculate the gradient of a scalar phi. Okay. dV would be the differential volume. Okay. And what would be the gradient theorem rate? This gradient to the surface integral as. So we had like GDT we had. But now we are talking about gradient theorem. So we have phi the scalar, and the gradient of a scalar is what we are calculating in the volume of the cell, delta V naught. So this could be converted into a surface integral, okay, phi dA. Gradient of a scalar is a vector quantity, and right hand side also vector, so dimensionally it is balanced. So gradient theorem relates gradient of a scalar integrated over the entire volume to be equal to sum of the scalar multiplied by all the vector differential areas on the entire surface. Now we use our mean value approximation, and if we say that gradient of phi of a cell centroid is representative of the entire cell. So that means for a particular cell, gradient of phi remain constant in that particular cell. So how I can write this gradient? So gradient of phi naught del V naught for that cell is summation of over all the faces of the property phi with area vector of the area of those faces. Okay. Yeah. Okay. So from here, gradient of phi naught will be 1 by del V naught summation of f phi af. Okay. Now, how you will write phi of f? So we need to kind of interpolate the phi from the phase values. Okay. From the phase values. Like if I say, if I have, like I will interpolate like this, phi of f will be phi of naught plus phi of 1 by 2. So suppose I have two cells like this. One cell is like this, okay, and one cell is like this, right? So this is P naught, this is C1. So here it is phi of naught, here it is phi of 1. Area vector is AF, okay, and this distance is suppose how much at this point? Del of R1, and from here it was del of R naught. This is your phase F. Okay. So this can be interpolated in this manner. I guess the interpolation we have done a lot of time. So linear interpolation means it is not an arithmetic mean. It will be a linear interpolation between these two cells. You need to get a factor f, which is basically the distance between the phase and the cell centroid. Okay. Correct. And from there, if you do all that kind of stuff, you take it as a phi of fs for these two cells, phi naught plus phi 1 by 2. Okay. I hope. So what actually is happening? We know the areas. We know what about the cell volumes. If you see, we know, and what we don't know, we need to calculate. We should understand this. So gradient of phi, we need to calculate this. Gradient of phi of 0 and the right cell. Okay, that is simple to do. That the cell center, what we need is it's a kind of a device of way of calculating the phi by interpolating them between C0 and C1 from to the faces from the cell values. Okay, so that is phi naught plus phi 1 by phi naught plus phi 1 by 2. Now, if I apply uh, like Taylor series expansion, basically I have connected. I would draw the line connecting the cell center to the face, that is delta R naught, okay, and delta R1 from cell center C1 to face again F. Okay, these are the two vectors that connect the cell center to the face centroids. And we can use a Taylor series expansion, not just in 1D, but a general Taylor series to relate the values of phi 1 and from phi naught. Okay, So if it were a 1D, we know that how to do it, right? Essentially, phi east is nothing but phi p plus dou phi by dou x of uh, phi of east, and also so of that stuff we can do. Okay. But yeah, what we can do there, phi of east is nothing but phi p plus dou phi by dou x at p delta x and so on. But here, what you will do, I cannot use 1D because this is connecting delta R naught. Okay, it's a connecting delta R naught vector, which is a particularly a vector. So we can use a general Taylor series extension and relate the phi f from phi naught. Okay, phi at the face from phi naught. So phi f will be what? So phi f will be phi naught plus gradient of phi naught, then dot into delta R naught, and so on. And with respect to phi, with respect to cell 1, it will be phi 1 plus gradient of phi 1 R1. Okay, all right. I hope it's clear. Still here. Any doubts? So we have calculated the values of phi at the face by interpolating from cell C0 and cell C1. Okay. So that would be phi f equal to phi 1 plus with respect to 1 gradient of phi del R1, and higher terms are there. Okay. So we do not have any confusion now. Okay. I've just completed what is gradient of phi at each and every cell. That is grad phi at 0 is calculated, grad phi at 1 is calculated. These are now known. So we started with only first term. We said phi of f equal to phi naught plus phi 1 by 2. Naught plus phi 1 by 2. But now we have an extra term, which is a second term in this Taylor series expansion. Okay. So now the general solution is that put the phi back into the equation and calculate what is improved cell centroids. Okay. First of all, what you will do, what do I mean from here is that put this value of phi f as phi f is phi naught plus gradient of phi naught delta R naught, okay, plus phi 1 plus gradient of phi 1 delta R1 divided by 2, correct? So for in doubts, this is vector as well. So we have written this phi naught and phi 1. Okay. All right. So we have substituted this value, and now we will substitute it back. Substitute it back. Okay. That is the I hope it is clear, no doubts clear. We got the phi of f. Okay. And now what you can do from here, you can put this back in this equation. Okay. The value of phi of f. So we have got phi of f. Okay. I hope no doubts. Who is there in anything? Okay. No doubts. Great. So the general solution is that we are using this phi of f back in the equation and calculated what is improved cell centroid values. What is improved cell centroid values? Here, gradient of phi naught. In this process, we have used an iterative scheme where we start off with a crude approximation for phi of f. We calculate it to calculate the gradients and use these gradients to improve the phi of f and then update the gradients. So this can go for a few iterations until we reach our convergence criteria values, convergence gradient values. But generally, you do not want more than couple of 2 or 3 iterations, which is sufficient. So essentially, the approximation for phi of f, that is a truncating terms in the Taylor series, that is making that we need couple of iterations for that because we are truncating these higher order terms here. Okay? That is why we need iteration. So 2-3 iterations are sufficient. That is need to be done in actual solvers. And if you were to write a general solution for this, so this is, we can say it's a gradient theorem approach. So you calculate your guess value. What is you evaluate what is phi of f from the phi naught and phi 1 self-centered values using the arithmetic average. And in the next step, calculated what is the gradients of phi. And this gradient of phi is at the self-centered using del v naught sigma f phi f f. So let me write gradient theorem approach algorithm. Is nothing but to get phi of f is phi naught plus phi 1 by 2. Then gradient of phi, substitute it back, is nothing but 1 del v naught summation of f phi of f a of f. Then you improve these values. Phi of f using phi of f that you have calculated, phi naught plus gradient phi naught dot till r naught, okay, plus phi of 1 plus from Taylor series expansion L of r1 divided by whole by 2. Use this updated phi of f and calculate it to go back to step 2. Use updated phi of f and calculate. Do the calculation. Go to step 2 and repeat. For the iterations. So it's a generic method and works on unstructured meshes. All right. I hope it's clear. Now we'll come to the least square method, least square technique. So first, you see what is the algorithm. Just take a minute and understand what I've written. Okay. All right. Now let's come to the second approach, that is least square method. Okay. So in here, this we obtain gradient of phi naught such that we reconstruct neighboring cell values from present cell values accurately. Obtain gradient of phi naught such that we such that we can from neighboring cell value from present cell value accurately. Okay. So how do we reconstruct this? Gives you the value of the gradient. So we want to calculate what is phi at cell 1 from phi naught using certain gradient values, gradient of phi naught. Now we want to calculate this phi 1 as accurately as possible. Then what would be like my gradient of phi naught? That is the idea. So essentially, we evaluate or obtain gradient of phi naught such that we reconstruct the neighboring cell value from the present cell value. Okay. Let us see one mesh configuration here. Let me see. Suppose something like this, something unstructured kind of scenario. Something like this scenario is there, where all places are connected. Suppose this is your C naught. Okay. So your value is given as phi naught. Okay. This is C1. This is suppose C2. So again, have done a mistake there. We draw once again. Suppose this kind of cell is whatever cell it is. So this is C2, C3, C4, C5. Okay. Then this is delta R1. Now it's from centroid to centroid, not from centroid to phase. Make sure that, like earlier, we have delta R2, delta R3, delta R4, and so on, delta R5. Okay. So a mesh we have not seen until now. It's look like this. We have a mesh here that is not necessarily have the same number of edges. Okay. Or it's refined or not. Let us call centroid C naught is there. We have neighboring cell C1, C2, C3, C4, and so on. This can be very different for your scenario also. So if you want to draw some lines here, okay, we have vector joining from center to center, delta R naught, delta R1, delta R2, and so on. So how I can write from the Taylor series expansion this time? Phi 1 will be what? So phi 1 with respect to phi naught will be phi naught plus gradient of phi naught or delta R1. Then phi 2 will be from gradient of phi naught, from phi naught will be gradient of phi naught delta R2. Okay. And phi 3, phi 4, and so on. All these values you will get with respect to this. To suppose you say phi j is equal to phi naught plus gradient of phi naught dot delta rj. Or these are the, you can say, mth equation term. Okay. So we have m equations. All right. So in 2 dimensions, how you will write? For 2 dimensions, you will write gradient of phi naught to be I hat dou phi by dou x naught plus j hat dou phi by dou phi x naught. If we say that we have a j, a neighbor of ij, what would be phi naught? Gradient of phi naught? Gradient of phi naught is, so here we have till m equations. Now in 2 dimensions, I'm saying the gradient of phi naught. Does it remains the same? So here delta R1 is not from, as I said, centroid to phase, it's from centroid to centroid. Delta R1 is I delta X1 plus J R delta Y1. Okay. Okay. So what we can say, we are writing gradient of I as I dou phi by dou X naught, J dou phi by dou Y naught. Okay. Now what you will write, gradient of phi dot R1 delta R1, because in expansion of Taylor series, which I have written here, you have this gradient multiplied with dot product with delta. So how you will write? So that will be dot product of these two equations. That is delta x1 dou phi by dou x respect to naught, delta y1 dou phi by dou y with respect to naught. Okay. So from here, delta x1 will be how much? Delta x1, this first term will be how much? Okay. How I can write this term? It's right hand down. So it can be written. What will be delta x1? Just think. So it will be like x1 minus x0, the x component distance between cell 1 and cell 0. We have this. So the product of gradient of phi plotted with r, in each of these term we have, as I showed you, we have this dot product in each of the n equations. So this would be basically delta x1 to phi by dou x naught plus delta y1 to phi by dou y naught. We have done this dot product to be this. Now my question is, how will I write the second term delta x1 dou phi by dou x naught plus delta y1 dou phi by dou y naught equal to what? Phi 1 minus phi naught. Okay, phi 1 minus phi naught. Simple. This dot product can be written as this goes here. So gradient of phi naught dot delta R1 can be written as phi 1 minus phi naught, which is the right hand side term. Okay. Similarly, for each and every term, you will write so delta up till delta x for the mth equation dou phi by dou x of naught delta mth phi dou phi by dou y naught is equal to phi m minus phi naught. Okay, correct. Now, if you observe, this is a system of equation. This whole is a system of equations. So how I can write this? Can I write it like this in a product form? Delta x1, delta y1, delta x2, delta y2, delta xn, delta yn. Unknowns are the gradients, dou phi by dou x, not dou phi by dou y, not. And right hand side terms are phi 1 minus phi naught, phi 2 minus phi naught, so on, phi m minus phi naught. All right. So what can we say? It is m cross 2 matrix. It is 2 cross 1 matrix. It is m cross 1 matrix. If you see, if you observe this, it's a overdetermined. We have two variables, these two variables, and we have m equations, more than two equations. It's a overdetermined system. Okay, where m is greater than 2. This m will be greater than 2 at least. Why? Because this is something which are connected to faces. Okay, what is the minimum number of faces a cell can have? If I take triangular cell, okay, at least it will have, this is the minimum kind of cell we can take. It has 3 faces, more than 2. So m will always be greater than 2. And m is greater than 2, always. Then you can take pentagonal cell, whatever kind of cell you want it to be. So it's an overdetermined kind of system. So if I want to make a plot of it, suppose like this, here I have phi versus x, dou phi by dou x gradients. But so we have lot of points. So what do we say? What do we do here? We want the over-specified system, over-determined, over-constrained kind of system. Because if you take two set of equations, you would get one solution, which will satisfy only these two equations and not the other ones. So because you have already come across such kind of systems many times, so when we do experiment also, we get into situations like these. If you are doing an experiment, you get some values here. Let us say phi and some x values. You got some values here. And you have to fit essentially your plot between these points. You have to find one equation, one straight line that passes through all of these lines. But you cannot find one equation that passes through all of these lines because you have too much amount of data. So what do we in this such scenario? You would find a you have to kind of minimize the error, the square of the error in the absolute sense. The square of the error, minimize, and we draw a line. We draw a line like this. Goes like this. Okay. we draw a line that would pass through any of these solutions. So it will not like satisfy any of the points, but it will, in a sense, that it will have a least possible error. So essentially, what I'm trying to say is that I've calculated an equation. This is my equation, and this is a least square fit. Okay, the least square fit line, which will not satisfy any of them, but it will have a least error if we consider one by one. If you consider least square fit. Minimize the error. Okay. So in fact, that we have this present situation, we have too much data. We have to calculate two components of the gradients, right, for the dependent variable, dou phi by dou x and dou phi by dou y from all these m equations. So what we set out to do is try to minimize this error and calculate what would be the gradients, which will be in the least square sense, and reconstruct the neighboring values accurately. What we are trying to do, we will do the remaining part of this minimization. Okay. So essentially, we are trying to minimize the error meaning from the line that we intend to fit between this data to minimize this error. So essentially, this matrix cannot be solved right. Can you invert it and calculate? No, essentially, you have to have any two equation and solve it. Let us have the names of this matrix like A, G, D kind of scenario. So suppose the matrix is, this is A, this is G, and this is D. Okay, A, G, D, fine. Okay, all right. So is the coefficient matrix, G is the gradient matrix, G is the delta phi's. Phi1 minus phi naught, phi2 minus phi naught. So we have to reduce this error, minimize the error in the equations we are working. That is del x dou phi by dou x x naught plus del y dou phi by dou y naught. Okay, equal to yj minus y naught, whatever point you are on. So what do I mean from here? We have this equation del xj dou phi by dou x of naught. Last equation, nth equation I'm writing del y by del phi naught is equal to phi j minus phi naught. Right? We need to, so the left hand side and right hand side should exactly match, but it won't exactly. There are a lot of other scenarios. So we will introduce residual error, that is Ri, which is nothing but, or Rg, sorry, which is nothing but the difference between the left hand side and right hand side part of the equation minus phi j minus phi. Okay. This is your residual error, and you want to minimize this. So this capital R can be written as j equal to 1 to m equation Rj square, error minimization of them. So I can say that this term is A, this term is B. This is A. This gradient is, I'm saying at A, and this is B. So what do I mean? I'll write it as summation of j equal to 1 to m A delta xj plus B delta yj minus phi1 minus, oh sorry, phi j minus phi naught whole square. All right. And you need to minimize this error. So what will you do? You will differentiate with respect to both the gradients. That is A and B. What will you do? Minimize something, we will equate it to 0. What do I mean here is that summation of j equal to 1 to n is 2 times A del xj plus P del Yj minus phi j minus phi naught del Xj equal to 0, right? This 2 you can remove, and similarly dou R by dou B equate to 0. So what you will get? J equal to 1 to M to A del Xj plus P del Yj minus phi j minus phi naught del of phi j whole equal to 0. Equal to 0. Now, just multiply all the terms. In this equation, multiply this with the whole of the terms. So you will have two equations now. Equation first is summation of j equal to 1 to m. That will be a del xj square plus b del xj del yj minus phi j minus phi naught del x equal to 0, j equal to 1 to m, a del xj del yj plus b del yj square minus phi j minus phi naught del y j equal to 0. Okay. It's a kind of del x1 square plus del x1 delta y1 plus del x2 delta y2 equal to something. Okay, that kind of these two equations are forming. So what do we have here is that we have made two equations here, these two equations. We have reduced the problems. We have two unknowns, we have two equations. So this is basically sigma j equal to 1 to m. Okay. We have two equation, two unknowns. I can write this in a matrix form as well. So how you will write? So suppose your equations are, I'm not writing a and b right in the terms of a and b. Suppose I just write directly delta x1 square, delta x1, delta y1 plus delta x2 square, because j is varying from 1 to m. Delta x2 square plus delta x2, delta y2, and so on. And then another equation will be delta x1, delta y1 plus delta y1 square plus delta x2, delta y2 plus delta y2 square plus so on. You can write in a matrix form as delta x1, delta y1, delta x2, delta y2, delta xm, delta ym. That is m cross 2. Okay. What will be A transpose? A transpose is do the transpose of it. Delta x1, delta y1, delta x2, delta y2, delta xm, delta ym. Okay. So this is m cross 2 matrix. M cross 2, and it is 2 cross n kind of. Okay. So how we can write our equation, set of equations? A transpose have in the right as well, phi 1 minus phi naught, phi 2 minus phi naught, and all those terms. Okay. So this set of equation now can be written as A transpose into A, which will give you again back these equations, these two equations. So that means if I transpose A, that would be my set of the two equations. Okay. This was multiplied with G or AGD, the gradients. So you have a set of equation like A transpose A, G is equal to A transpose D. So D is 5 minus 5 0, 5 2 minus 5 0, and so on. So this was 2 cross 2. This was 2 cross 1. This was, so that will be again 2 cross 1. 2 cross 1 kind of system. Now we have two unknowns, two equations. All right. You can get the values of the gradients which you wanted from the least square method. So it doesn't matter how many phases you have. It's a 2 by 2 kind of system now. You can calculate this and calculate it inwards and calculate what is the gradient values. So that means for every cell, you will go and solve the system once and get the gradient values. And then the G thus obtained would satisfy one of these equations. None of these equations will only satisfy these equations and least square equations. Okay. That is the sense of the least square method. And what would happen if you work for the Cartesian mesh uniform cells? Will it work for a structured rectangular mesh? Would this method work? Let us say for a Cartesian mesh that is uniform, Cartesian structured, or it will only work for unstructured mesh. So then what will happen if you have a Cartesian structured mesh, which is also uniform? What will happen to the matrix A? What about delta x1, delta x2? So all are the same. Then what will happen to the matrix A? Would it become singular? Then you said it will work for Cartesian mesh. And then we are saying it will become a singular. And then there is a catch. All right? Then there is a catch here. What is the catch? Think about that. Catch is if you do the dot product for the rectangular structured mesh. Okay. So here, this direction it is pointing, and here in this direction, opposite direction are they are pointing. One coefficient will be positive, one will be negative. Positive, negative, positive, negative. So it won't give a determinant kind of singular kind of, okay, sorry, singular matrix of the coefficient matrix. So the way we have drawn the vectors are all different in the unstructured mesh. Okay. But in structured mesh, we essentially know. So eventually it will work it out. And yes, in detail, the prof is also discuss about this. But to give a brief that it will definitely work for structured mesh. Okay. Just the coefficient will be one will be positive, one will be negative. Okay. Any doubts? All right. No doubts? Okay. Just give me a minute. Okay, let's start. Next topic. So far we discussed the gradient calculation method, Green Gauss method, and least square approach. Now, now we'll start with secondary gradient influence on the coefficients and implementation of unstructured solution algorithms. So even in the, what we can say, so far, like up till now, we have been seeing that only the secondary gradients will make the solution may not be bounded, that the guarantee that the solution is bounded, but will be taken away if you have secondary gradients. That is what we have been saying so far. But we have not actually proved this thing or looked at why it happens. So that is one thing we are going to see today. Other thing is that we are going to look how do you implement a solution procedure or how do you program it to the solution procedure for solving a diffusion equation on unstructured meshes. It doesn't matter whether it's an orthogonal mesh, non-orthogonal mesh. So only if you have, as long as you have an unstructured mesh, you can implement it. And what is the way if to be done? Another thing we are going to do today is that you can say boundedness is not guaranteed even if you have the source terms are absent in the context of unstructured non-orthogonal mesh. Why is it boundedness not guaranteed? After finishing that, we will move to how do we program the diffusion equation on unstructured mesh. Okay. And it is the same way as we do for the structured mesh, or it is something different. So all this thing we will kind of look and maybe we can code these things if we have time persist. All right. So let me write the heading. Secondary gradient influence. So if you have a curvilinear kind of mesh, the some curvilinear kind of mesh, you have a cell P, but then it has north, south, east, west, the northwestern zone. So it's a curvilinear form of grid. We need to calculate rho phi by. So here these lines are theta is equal to P constant, and here these lines are theta is equal to constant. We want to calculate dou phi by dou eta at east phase. That is this phase. So calculate dou phi by dou eta at east phase. There are two ways. One approach is using phi A and phi B. These are the phi A and phi B. If you have these values. Another is by interpolating all these dou phi by dou eta at P, dou phi by dou eta at east. Here and here. Okay. All right. So phi A will be how much? Contribution from the neighboring cells. So phi A will be 1 by 4 phi P east west, phi P east, southeast, and phi south. So phi A is here. This one. There are these points as well. This is southeast. So A will have a contribution from P, east, south, and southeast. Okay. Depends on number of neighboring cells. Never divide by 4. The number of neighboring cells. Phi P plus phi E plus phi southeast plus phi south. Similarly, phi B is covered up with northeast. North, northeast, P, and east. 1 by 4 by east, phi of northeast, phi of north. And what will be gradient rho phi by rho eta at east? Now, other way is if you have B and A values, which you have calculated now, that is phi B minus phi A over del eta. We put the values phi B minus phi A here. So you will get 1 by 4 del eta phi northeast plus phi north plus minus phi of south plus phi of southeast. Okay, this is we have got at the east field. Correct? North is north, south is south. So what do you notice in the above equations? Coefficient of phi s and phi of se are negative. So that will create oscillations and boundedness is not guaranteed. It might give a negative solution. So an increase in these values could lead to decrease in the values of phi. So that is the influence of secondary gradient. So actually, negative coefficients lead to oscillations. Boundedness not guaranteed. Okay. So actually, how you write the secondary gradient, if you remember from the last lecture, minus del f af dot af dot e zeta. Here e zeta dot eta and the gradient dou phi by dou eta of it. The magnitude of secondary gradient is directly proportional to dot product of e zeta eta. So for good quality meshes, this will be very small. That is why we prefer to make our meshes in the form of a structured meshes, so that dot product will be zero. Okay. E zeta eta, they will be orthogonal to each other and it will be zero. There will be no influence of secondary gradient. Okay, in case of orthogonal mesh. The influence of secondary gradient is small for good quality meshes. Bounded is not guaranteed, though it depends on the quality of the mesh as well. Depends on quality of mesh. Now we'll see how the implementation of diffusion on unstructured meshes. Okay. So how does one implement the solution of diffusion equation on unstructured meshes? So let's take a look at first the structured mesh coefficients. Okay. So you mesh like this. If you observe, there will be uneven spacing. This is a point of consideration. This is the west node for it. This is the east node for it. This is east node. And this is west space. So east space. And this is west space. And this spacing is how much? LXP. And this is direct C. Okay. And this will be how much? Okay. between the two cells. So we have cell 1. This is our cell 1. Similarly, if we have a grid, same grid, grid is same. I'm just making another figure. Same, exactly ditto I'm making. Now, at this time, the east cell of this will be my cell 2. Okay, cell 2. So for this will be the west, and this will be west-west, and this will be east. Correct? And this will be west face and east face for cell 2. So how you can write A east for cell 1? Your A east, cell 1 east is gamma E delta Y by direct C. Gamma E delta Y by delta Y is the width. Direct C. And for cell 2, your A west will be gamma W delta Y by del XW. Correct? So eventually, for this cell, this is the east face. For this cell, this is the west face. But the face is same. This is we have manually defined. Actually, for the grid, it is the same face. So we can say that A east and A west are equal because both cells have the same contribution. That means A east is equal to A west. So for that particular phase, which is west for cell 2 and east for cell 1, we can say that AF is equal to gamma F del Y by del XF. Okay. That will become A east for cell 1 and A west for cell 2. Any doubts still here? Oh. So this suggests associating the coefficient with the faces rather within the with the cells. This associates. This suggests associating. The coefficients with faces. Rather than with cells. All right. So how to discretize the equation? This equation. Multiple times we have written this equation. For any phase F, the flux grad del phi delta grad phi is leaving the cell P and entering the cell E. So in unstructured mesh context, what is leaving is entering the another cell. What is leaving the cell C0 will be entering the cell C1. Okay. So this is a consequence of statement of conservation of flux. So associating the flux with the phases rather than with the cells require maintaining a phase-based structure. And this will also save time from multiple calculation of the same quantity. Okay. So we are working with a phase-based structure. So what we can say, A and B is gamma F AF on delta X, and A and B gamma F plus zeta AF dot AF on AF dot E zeta of. We can calculate A and B for a phase F that is between cell C0 and C1. Okay. So A and B for C0 is equal to A and B for cell C0, and A and B for C1 is equal to A and B for cell C1. Do you have any doubt, please ask? Okay, no doubts. So what we can say, we calculate A and B for phase F. Okay, between cells not and C1. So if you have structured mesh, A and B is gamma F AF by del XF. We have already seen, but in unstructured mesh, A and B will be coming from your primary gradient coefficient, that is under this one, and the secondary gradient. So, sorry, not secondary. This is from structured mesh, and this is unstructured mesh, and this is primary gradient. Okay, on the primary. So we can calculate A and B for phase F, that is between C0 and C1. Thus, we have calculated for cell P, cell east, and then we can calculate for a particular phase. Okay. So essentially, there are two different. This is A and B for cell C0, A and B for cell C1. Now we are going to see cell by cell. We are going by phase. We are not going by cell by cell. We are going phase by phase, and we are accessing the cells from the phases. Here, what should I write? A and B of C0 is equal to A and B. Okay. For cell C0, cell C1, A and B of C1 is equal to A and B. Okay. Now, if you have multiple amount of cells, what do you mean here? Suppose you have this structure of mesh. Something unstructured. Thinking this like a structure is there. So this is C naught, this is C1, and this is C2. Alright, this is C3. So suppose these are connected from phase 1, phase 2, phase 3, and so on. Whatever amount of the cell C naught has AF1, cell C naught has A and B C naught, that is AF1 in the phase 1. C1 will have A and B from C1. Okay, that is again phase 1. So for C naught and C1, the space is common. So A and B will be same. For again C naught and C2, the C naught, A and B C naught will be AF2 this time, and C2 and BC2, that will again be AF2. Both will be equal, sharing the same phase. Okay. All right. So this is because both AF and magnitude and sign are same for A and B's, because AF and E zeta reverse direction from when move from C1 to C0. Magnitude and sign are same. Visiting all the phases completely, then calculating the A and B for the cell. One by one, you will visit all the sets, and then you will calculate for them. Okay. I hope it is clear. Suppose if you have a phase like the C0 and C1, so this is your C0, this is your C1. Okay. So for C0, the area vector is here, pointing here. And for C1, the area vector is pointing here. Okay. Then theta direction will be same for both. Theta, eta, both will be same for both of them. But the connecting cells, the zeta direction will be, so for here, the connection direction is E theta. Okay. But here will be E theta. All right. This is your phase F. And this is your phase F. All right. And these are the values A and B. And all right. Any doubts still here? Okay. No doubts. Think once in your mind. Then I'll discuss further. So what, basically, we are not going cell by cell. We are going phase by phase, and we are accessing the cells from the phases. So we found a way to do this thing. Now let us say we have an unstructured mesh that is shown here like this. And something like C0 is the primary cell we are focusing on. Then we have the three phases F1, F2, F3 connected to C1, C2, C3. That means when I calculate F1, I need to assign the value of A and B for C0 and A and B for C1. We mean A and B for C0 and C1. Then A and B for C1, we mean C1 to C0. So for example, this A and B can be 0, 1, right? That is basically coefficient of 0 for one cell. Similarly, there can be this could be a coefficient of 1 from first cell to 0. Assign this for both the cells. Similarly, then we go to the next phase for F2, okay, and then to the F3 and so on. So we see that here is the magnitude and sign of A and B same for both the cells. We are not changing because phase is same, sharing the same phase. And we are assigning the same value to both C0 and C1. Similarly, for F2 also, C0 and C2, we are assigning the same. And it's happening because we calculate A and B from this cell. And we go here, here there are some certain things that are changed, right? For example, if you are like F point away for cell 1 to cell 2, cell and then to cell 3, then A and B for that particular cell will change. Okay. So if we have suppose C0 and C1 here, so black lines are indicated, the black arrows here. If you see in my case, I don't know, it's in dark mode, it will show the white line, whatever. So for C0, it's orange, I'm saying, and for C1, it is white instead of black. So the area vectors and directional vectors all are showing. So we are calculating A and B, that is basically we are calculating for that particular phase F, and we are setting on C0 with respect to C0. Let us assume that we are calculating with respect to C0 first. For eta point in this direction, similarly, zeta point in that direction, etas are same, zetas are opposite, and area vectors are opposite. Okay. Any doubts? Basically, we are interested in AF dot product with AF and AF dot product with E zeta. AF to E dot E zeta here for unstructured mesh. Okay, A and B's are computing from here. All right. AF and E zeta dot product is required. You have to look at when you calculate from C0 with respect to the C0 cell. Okay. AF and zeta for C0 is basically pointing in this direction of orange pointer. Suppose they are not orthogonal also. But when you are sitting from C1, they will flip the direction. Dot product would come out to be the same contribution, whether you are setting from C0 or C1. So you calculate because both point for C1, E zeta is here and AF is here. Dot product is same and magnitude is same. And for eta, C0, this and this are same. Okay. The magnitude and direction are same. So whatever cell you want, you can put to calculate the dot product. So what we need to do now, this is for two cells. So we will visit each and every phase in this session. Once you visit each and every phase in this session, after completing all this, complete the calculation of ANB for all the cells. For example, this cell has AP, that is 0. It has 3 neighbors, if I have shown 0, 1, 0, 2, 0, 3. So they have 3 phases, F1, F2, F3. Once you visit all these phases for every cell, then the neighboring coefficient would have been already been right. You would have filled the neighboring coefficient for all these cells. So if in the original cell center or cell-based approach, you would go to every cell and populate the neighboring coefficient for it. But in this case, you are visiting the phases and populating in pairs the neighbor coefficient for those cells which are shared, which are sharing the phases. So the pattern is different. But when you finish visiting all the phases, you have already assigned all the cell values coefficients, cell neighboring coefficients. And this is faster because you're not calculating again for every cell. And also you are assigning both of them at once, right? And going here and calculating 3 and coming here and then calculating 3, like from point 1 to point 2. Okay. So by this time you finishes 3 phases, you actually assign 6 coefficients. Okay. All right. So what about the secondary gradient terms? How to collect this term from the cells? Because this is also associated with the phases. If you remember, there is a dot product of AF dot E zeta. So where does that go? Because in secondary gradient, which is written as AF dot AF dot E zeta E zeta dot E eta. So 5 and 2 and that is again we have a dot product here. Okay. So again you have to go to every cell and calculate it. But that is not the motivation we want to calculate from the phase database structure. The secondary gradient is also asset because secondary gradient is also associated with the phase between the cell. That is why we write the secondary gradient. Also, this is associated with the phase. We have to computational time. And if you calculate it at once and assign it to the both the cells, which share the phases. Okay. So how do you solve secondary gradient goes into the B term? The B term also contains few other quantities such as other fluxes or whatever boundary conditions you are giving. So therefore, instead of assigning, add to the existing value of the B terms here. For cell 0, suppose I'm writing for cell 0, V naught will be V naught plus secondary gradient in the right hand side term. And cell C1, C0 and C1. So B1 will be B1 minus secondary gradient. Okay. So as a different side, one time it is added, one time it is subtracted. You have to think. Because you can think that is pretty simple. The dot product just flips out. That is why. If you see the in the dot products, this dot product I'm talking about, this dot product flip out because for cell C naught, E zeta and eta has a dot product this, but for cell C1, E zeta, but eta is remaining there only. So the direction changes. That is it. So we have list of all the faces in a mesh. The cell number of these faces are also known. We have list of cells in a mesh. We calculate A and B for cells by visiting all the faces. Okay, visiting each cell and calculating the AP. Then we will calculate visiting each cell and calculating the second SC contribution, second source term contribution as it follows. And of course, secondary gradient needs a gradient calculation at cell centroids. Then equation have to be modified to incorporate the boundary cell as well. It's just so far for the internal cells. So basically, what is the algorithm? We give the initial guess for phi at cell centroid, calculate the gradients at cell centroid using gradient theorem. Coefficient calculations happens. We traverse through each and every phase from 1 to n phases. Calculate A and B, assign A and B, C naught and C1, sharing the common phase. Calculating the secondary gradient. Here, it will come into the B terms, B naught plus secondary gradient, and B1 is equal to B1 minus secondary gradient because of the flipping of this. Okay. Then traverse through each cell again for calculation of AP and B's. Solve this equation AP5P summation of A and B phi and B plus B to obtain the Gauss 5P's using the Gauss Seidel solution, and then check for the conversions. If it is not converged, then again go back to the step number 2. Okay. Everything has been discussed by the prof in the lecture videos, so you can take that from there. So here we finish the chapter with the diffusion part. Now we will introduce discretization of steady convection equations. Just give me a minute, guys. Okay, let's proceed. So steady convection equation. Start the topic in the next chapter. We'll be dealing with discretization of steady convection equation. So if it's steady, so unsteady term will go away. Convection, diffusion. Yes. So we know the equation looks like del dot rho u phi. This is your convection term. Del dot phi. Where u is nothing but the velocity vector ui cap plus pj. So we'll assume so far now that u is known to us, although it is an unknown, but we will assume that. All right. So we will integrate this equation because we are dealing with FVM. Integrate over the control volume. Integrate over the control volume. We have seen this part so much till here. So many tutorials, so many lectures we have seen till here. What is new thing is here is the application of Gauss divergence on this one. Okay. We are assuming that U bar is known to us. Make sure that. What will you get? That will be rho u phi dot dA over control surface. Is the thing, but this right hand side we have already seen multiple times. So u of f dot af. Okay. So your grid looks like this. Suppose uniform grid. Something like this. So this is a cell P. This is north, south, east, west. And this is your y. This is your x. All right. This is your east face, north face, west face, and south. Right? This is your delta x. And this is your delta y. Two-dimensional grid. We've already seen this kind of grid. So here it is transporting by convection also. All right. So here, the term this can be written as again summation of all the faces dot af. Okay. Convection property term. So this term LHS can be written as so phi of faces AF. All right, this is need to be calculated. Area in east, you know that it is del y I cap I hat. Area is west is minus del y I hat. Already we discussed all this thing. Del x A hat. Area south is minus del x A hat. Okay. U vector is nothing but ui plus vj. The dot product of each face will be, if you do rho u phi of east with a east, so that will be rho u phi del y. Rho u phi of east will A east is del y. Okay. So what I can write it as the rho u east into del y into phi of east. Okay. So this term can be written as mass flow rate, FV, which is nothing but okay. What I can write it as FV phi E. All right. Diffusion term you already know. Your diffusion term multiple times we have done this. Can be written as for each phase, suppose gamma E east, rho phi by dou x of east is equal to gamma E delta y by del x east phi E minus phi P. Okay. So I'll say that this term is nothing but dE. Okay. So that is diffusion term. dE, diffusion flux basically. Phi E minus diffusion that was mass flow rate, and this is diffusion term flux. Okay. Correct. Now we will define one term, that is ratio of FE by DE. FE by DE. What is FE? Rho U. And what is DE? Gamma del Y by del XE. Del Y by del X. So what can I write? Rho U del Y, sorry. If you observe del Y and del Y cancel out, it will be rho U del X by gamma. This is called as Beckley number. This is called as Beckley number. So phi, when we are writing the phase value phi in terms of cell values, this determines the convection scheme. And gradient dou phi by dou x, we already know, linear profile assumption. Okay. So you are saying that Fp phi E, how you will get the phi east. Okay. So by linear, once a convection scheme is decided, we write the similar equation for both west, north, south faces, correct the terms, and finally discretize for every zone. So how you will calculate this phi E here? This is a question. This is a convection scheme. This we already know. We have done through linear profile assumptions and all. Okay. So far. But for this, suppose we are using a central difference scheme. Central difference scheme, which says that phi at the east phase for a uniform mesh, it is summation mean of phi of east plus phi of e by 2, assuming phi varies linearly. Okay, assuming phi varies linearly for uniform mesh. Okay, assuming phi varies linearly. Okay, we can write our Fe to be convection term Fe phi to be Fe, that is Fe is Fe phi e plus phi p by 2. All right, phi e plus phi p by 2. Similarly, for all the other faces, you can write east face, west face, north face. Okay. So when I'm writing complete equation for east face, what will I write? Gamma graph phi east dot east, okay, minus rho u phi east dot east is equal to E del y by del xc by E minus phi p minus Fe by E plus phi p divided by 2. Similarly, we'll write for west phase, north phase, south phase, difference of these two terms. All right, will here any doubts? Similarly for other phases. Okay. So this is nothing but dE by E minus phi p minus Fe by E plus phi p by 2. This is for east phase. Similarly for west phase, phi p minus phi w minus Fw phi p plus phi w by 2 T north phi north minus phi p minus F north phi north plus phi p by 2 T south phi p minus phi south minus F south phi p plus phi south by 2. Okay, plus therefore your whole equation will look like something like this: Sp plus Sp phi p del v equal to 0. This is your whole equation. Okay, so this is in the term of AP phi p equal to summation of A and B phi and B plus P, where A east, A north, A west, south. We'll see your A east is DE minus FE by 2, D minus FE by 2. Okay. A west is EW plus FW by 2. A north is DN minus FN. And A south is CS plus FS by 2. Okay. Now if you observe, these two coefficients can have some negative value, but these are positive. Okay. All right. But I'll write AP. AP will be DE summation of AE, A west, A north, A south. So how I'll write? See here. AP is DE plus FE by 2. And this plus FE by 2 can be written as plus FE minus FE by 2. Okay. So I can write it as plus FE minus FE by 2, or minus FE by 2 plus FE. Same meaning. Okay. Correct. So we will have this as A east and an additional term FE. Similarly for A north, A south, additional terms will come. So I'll write my final output as A east plus A west plus A north plus A south minus SP del V plus the additional terms, those were FE plus F minus F west plus F north plus F south. Okay. And your B is SC into del B. Okay. Clear? No doubts? You have defined what are FEs, what are DEs, what are the coefficients A west, A east, A north, A south, and AP, what is B. Okay. Now, what can looking this, you see that AE and A north, as I said, can provide you with negative values, which will eventually create a boundedness issue. It will not guarantee the boundedness. Okay. So when the vector, your velocity vector is always positive. So that means your FEs, rho u, rho east, rho u west, rho u all will be positive. So all FE, FW, F north, F south will be always be positive. Okay. So if AE is always positive, if you want AE to be always positive, that means DE minus FE by 2 should be greater than 0. Correct? So that means FE DE should be greater than FE by 2. Correct? All right. So 2 DE greater than FE. But if it's a reverse case, if it's not like this, if it's FE is less than 2 DE, sorry, FE is greater than 2 DE. If it's like 2 DE is less than FE, then it means AE will be 0, less than 0, negative situation. Then in such scenarios, cargo criteria condition may not meet your, you can say that boundedness can hamper. All right. And one more thing, the Peclet number which we have defined, that is, if you see here, which was FE by DE is less than 2 for this scenario, I'm saying. Okay. Here, A east is greater than 0. Here, A east less than 0. Okay. That means your Peclet number cannot have a value greater than 2. So therefore, Peclet number will always have a value less than 2. So when you are using your central different scheme, we were using central differencing scheme. Yes. So that means you cannot have flow with the higher Peclet number greater than 2. Right? So I'll write it in a precise manner here. For A east to be greater than 0, that means DE minus FE by 2 need to be greater than 0. DE is greater than FE by 2. Okay. So 2 FE by DE, which is nothing but your Peclet number. Therefore, Peclet number is always less than 2 for central differencing. Yeah. Also, one more point. If A east is less than 0, this implies boundedness may not be guaranteed. Also, cargo criteria may not satisfy. Okay, we've already discussed what is cargo criteria. Okay, all right. So we'll see instead of central differencing scheme, what other schemes we will use in coming tutorials. I hope there is no doubt. We have covered a lot of things in today's tutorial. Okay. All right, see you in the next class. Maybe you can leave. Thank you.